So we use a lot of energy as a planet. By 2050, our average power consumption will be 28 terawatts. That's 12 zeros after 28. The only resource that's available to supply to this demand is the sun. We have about 100,000 terawatts striking at the Earth's surface when the sun is shining. And after we subtract away the ocean, mountains, and so forth, the usable energy is about 600 terawatt. So that's still in far excess of our utilization. But there's a problem with the sun. It doesn't shine all the time, and it doesn't shine everywhere. This is a picture, a photo from the International Space Station showing the United States half in daytime and half in nighttime. This is one problem of the sun. The second problem with the sun is that it doesn't shine where we need it to shine. So we have here London, Tokyo, and Chicago. So if you've been to these places or live in those places, you know that the sun is not abundant. Yet these are giant metropolis in which we have huge population center. So you might ask, how about Texas? There's plenty of sun in Texas, right? That's not entirely true. Even in the summer, you have thunderstorms that limit the availability of the sun. So the big problem with solar is that it is not available when and where it is needed, at least not all the time. So the vision we have is to make energy available when and where it's needed. So roughly speaking, we can divide it into several processes. One, we have a carbon-free source, like the sun. We have to first capture it. Then we have to think about how to store it. And that's going to be the bulk of my talk today. We have to deliver it, and we have to utilize it. We already do this today pretty well. We can take solar panels as a way to capture sunlight, turn that into electricity. We can store it in batteries, like our iPhones or electric cars. We can deliver it using the conventional electric grid, and we can use it. But the problem lies with storage. It is not a perfect mechanism. With batteries, it's rather expensive and it's heavy. Actually, we're carrying away dead weight with batteries most of the time. We're not carrying the energy we need. It's mostly just things that's inactive. You're not storing the energy. Moreover, battery does not store electricity for a long period of time. If you look at your iPhone and so forth, it only lasts for maybe 30 days or 60 days if you don't charge it. So you lose charge over time. What we need is a medium to store energy that is long-lasting, dispatchable, so we can bring it to wherever it is needed anytime, whether the sun is shining or not. So I want to introduce you to the concept of what we call solar fuels. Fuels such as ethanol, methane, which is the biggest component in natural gas, or hydrogen is a great way to store energy. You can dispatch it whenever you want. It is very high energy density, and it can be derived directly from the sun. You can imagine we can take molecules like water or carbon dioxide. We can put the sun to it, take them apart, reassemble them into these energetic molecules such as ethanol. We can store it in their form. We can transport it in the pipelines. We can use it. And when we burn these materials, what we get? Water and CO2, and it goes back right to the top of the loop, and we restart again. It is a carbon-neutral energy cycle. So this is where we aim to be, but we're pretty far from it now, but this is the way of the future. So let me talk a little bit about how to turn water into hydrogen and oxygen. Here, hydrogen is your fuel. We call this sometimes the reverse combustion process. Combustion is the other way around. You take hydrogen or any other form of fuel, you put it with air, and you burn it, okay? And you can get power out of it. So this is the reverse process. You can imagine that it is an uphill process. You are spending energy, you're pushing the water molecule uphill, as shown on the slide, and you want to get over this barrier. It's about 1.2 volt. This is roughly the voltage of a AA battery that you have. It doesn't sound like a lot, but it is very hard to achieve, to get this 1.2 volt needed to dissociate water into hydrogen and oxygen so that we can use it when and wherever we want. So in this process of dissociating water and taking it into a form of a fuel, it is inefficient. Okay? And I'm going to talk about a couple of things that we're doing on Stanford to make this a reality. One of the biggest challenges with taking sunlight and storing as a fuel is we can't use the entire solar spectrum very well. So on the top of the screen, you see the various colors of the sun. You have UV light, ultraviolet light, you have the visible light, and you have infrared. Solar cells today can take the visible light very well. It can also take the ultraviolet light very well, but it can't take the infrared light. But it's actually a bulk part of the solar spectrum. And if you take a look at the availability of power as a function of the color, the wavelength of light, you will see what the problem is. Solar cells today can only take a very small portion of it, like the one shown in red. Everything else is lost as heat. And because solar cell efficiency decreases with heat, you will have to cool it in order to maintain efficiency. So all this energy that is not being used and is now turning up as heat is discarded in the system. So we can't use that very well. But we now have developed a new system at Stanford to help us take not only the light energy, but also the thermal energy. So we can take the entire solar spectrum, whether it's coming as light or being absorbed as heat, and put all those energy toward rolling that water molecule up the hill so that we can dissociate it into hydrogen so it can be used as a fuel, store it, and dispatched. Another big problem with solar fuel is it often takes very rare materials to perform the process. Often, it takes materials like platinum or iridium. These are among the rarest material on the planet to carry out this pushing uphill process with light. What is happening when you shine light on these materials, the electron starts moving around, and the electron is zapping the water molecules and allowing it to be dissociated into hydrogen and oxygen. But you want to do it with the material that is abundant. And what we're looking at is using material iron oxide. So this is essentially a form of rust. It gives rise to the red color of rocks in southwest United States. It's one of the most abundant material. The problem with this material is that these electrons, when you shine light on it, doesn't move very fast. So you can extract the energy very efficiently. But it turns out that if you give a little bit of heat, these electrons start moving much and much faster so that it can eventually reach the water molecules and turn that into storable fuel. So that's what we've been looking at for the past couple of years on taking sunlight, water, and sometimes even carbon dioxide, and turning that into a fuel so we can use it when and whenever we want. So you might ask one question, well, how do we get both heat and light at the same time? After all, if we stand outside, we don't get to very high temperature. But it turns out if we take a magnifying glass, we can focus sunlight to a smaller spot. And that allows us to achieve simultaneously the intensity of light and also heat. This is a conventional solar cell. You take light and you shine it and you convert to electricity. But imagine now you have a way to focus the light with mirrors. And now you have a smaller solar cell, so you decrease the cost because you're doing more with less. But the problem with conventional solar cells, you have to cool it in the process because the heat decreases the efficiency. But now imagine using a process that can positively be enhanced with both light and heat. Then you can take both, convert it to useful energy without the cooling. So now you eliminated part of the system which was limiting the cost. So hopefully giving you some idea of the possibility to store sunlight in terms of fuel, turning water, carbon dioxide into fuel, and making the sun available when and where it's needed. Thank you.